Hello there. After the discussion of this virtual work and the virtual displacement, now we are trying to apply for the real kind of applications, right? So everywhere there is a real kind of applications are available when the body is in the equilibrium condition. Suppose you can take a building where it is going to be existed on its own foundation, but it is not going to be moved in the upward direction or in the downward directions. But rather than if you apply the principle of virtual work, we can make that the object is going to be moving in the downward direction, or maybe to the left side or to the right side or to the upward direction also. On that basis, we can find out the virtual work from that part. So on that basis, I am going to be giving one of the practical example over here. So that's going to be case 1 I have taken. So in this case, A and B is going to be the one bar, the end A and the B. So then what will happen? I was hinged at a C at the point at a C. So then what will, in this case, and I was trying to apply the two types of the forces. One is at the end A is the P, and at end Q, that is end B, there is a Q force is going to be acting. And can you see here, the geometrical distances between the point A and C is the A. From the C to B is going to be the small b distance I have mentioned. So now in this case what will happen? So in this case, that magnitude of the P and the magnitude of the Q we need to be calculated. If you are using the equilibrium equations, so that means the equations of equilibrium conditions, what is the formula we are using? And I am going to be removing this C, but rather than this one directly I am going to be taking the moments, equilibrium equation, that's going to be moments at the C I am going to be taking, that is equal to 0. Right? When it is going to be 0, so then how we are going to be calculating? And we are going to be considering the counterclockwise is going to be the positive, the clockwise is going to be the negative we are going to be considering. So in this case, the Q force is going to be acting in the clockwise direction and the P is going to be acting in the counterclockwise direction. So then on that basis, the P into the normal distance, this is going to be your line of action, and this is going to be the distance between the radial distance between your point of observation to the line of action, that is going to be the PA. And then it is going to be moving in the clockwise direction. The minus of Q into B is equal to 0 I am going to be taking. So from this equilibrium equation, we are going to be calculating the force P at the Q. That means we are going to be calculating the magnitude of any of one of the force, or we are going to be calculating the direction of the force, or we are going to be calculating the line of action of these forces, at what distance they are going to be acting also easily we can calculate it. But now how we can apply this principle of virtual work for this condition? So as we know, the total work acting on your body because of the group of the forces are acting is equal to 0. So we are applying the principle of virtual work method for this to find out that part. So now we are applying the principle of virtual work. So the same diagram I do have taken, this is the end A and the B. So then what will happen? Because the body I am going to be considering at the equilibrium condition, there is no displacement. But I can apply the imaginary displacement to this body because of these forces. So then how I am going to be taking here? I am going to be taking the displacement of this axis of this member I am going to be considering in this direction. So can you see here? So that means the body at the initial conditions, that's going to be in the horizontal direction. But because of this imaginary displacement, and then I am going to be shifting to this position. So then this is going to be your inclination, it is happening. So that I am going to be saying this is going to be your del theta. The del theta is going to be the very small angle it is going to be generating because of the imaginary displacement. And here also it is going to be maintaining the same kind of angle. So then after the small displacement, the body is going to be shifted from A to A dash, and here B to B dash it is going to be shifting. But in this case what will happen? There is a curvature is going to be generating over here. But for our simplicity purpose, because del theta is going to be the very small, always I am going to be considering B and B dash always normally to the initial position of the bar. And here A bar is always normally to the initial position of the bar we are going to be taking. So now we need to find out, this is going to be your displacement is going to be taking place because of the force P, and here is the B dash is going to be the because of the Q force, the displacement is there. So now I am going to apply, I need to find out what is the displacement of A dash. and here is the del theta is available, and from here to A to C the distance is going to be available. If I am going to be taking the tan del theta, so tan del theta, if I am going to be taking for the triangle of A dash C, right? So tan del theta is equal to opposite side by adjacent side. I am going to be taking A dash by AC, suppose if I am going to be taking. So then in this case what will happen? We need to find out the A dash. So from this one, A dash is equal to tan del theta is going to be the very small, and then only we are going to be considering only the del theta. So AC is nothing but the geometry, that means the distance between the point A and C. So that is equal to A into del theta. I got it. So that is the displacement is going to be in terms of the A as well as the del theta, because those terminologies we know. That means unknown terminologies we converted into the known terminologies. When it comes to the point B, so the triangle B dash C. So here in this case also this is the small displacement, and B dash, and this is the BC is available. So that's going to be tan del theta. Tan del theta is equal to B dash by BC. I am going to be taking from this one. B dash is equal to B into del theta. I will get it. So this way the virtual displacement I was calculated from this one, the small displacement d theta here, angular displacement, and the known distance of the BC from this one I have calculated. Now what is the definition we have taken? The total work done on the body is equal to 0 when the body is in the equilibrium condition. That means the total work done is equal to, the total work done is equal to 0. So then what is the total work done in this case? In this case, can you see, and when the force is going to be P acting in the downward direction, the displacement also in the same direction. So then the sign convention is going to be the opposite. But in this case B dash is there, so the QE force is going to be acting in the downward direction, but the displacement is going to be taken in the opposite direction. Then you will get the negative of that part. So then what is the total work done in this case? In this case, work done due to the P1 and the work done due to the Q we need to be taken. The total work done is good. I am going to say W D work done is, that is equal to P into A dash minus Q into B dash. In this case, the displacement is acting in the downward direction. The force is acting in the downward direction. The displacement is in the upward direction. Now we are substituting A dash is the virtual displacement, even though the body is in the equilibrium conditions, that I am going to be writing here, that is equal to 0. That's what we told, the total work done is equal to 0. Then the P into A dash is going to be what you call, that is going to be A del theta minus Q into, that's going to be the B del theta we are going to be taking. So that is equal to 0. So then I am going to be equating these two parameters. That's going to be the P A del theta minus Q B del theta is equal to 0. This del theta will going to be cancelled out. Then finally from this equation, P into A is equal to B into the Q into small b I am going to get it. So there we can see that equations what we got it from the virtual work method, and the same also I got it from the equations of equilibrium, or the equilibrium equation, that's going to be PA minus QB, that is equal to 0. Then this parameter, if I am going to be taking the PA is equal to QB, we are going to be getting. This is the way, the principle of virtual work we are using to calculate the unknown forces in this member. That means either maybe the external forces or maybe the internal forces of these members also we are going to be calculating. Now we will see one more example how it is going to be. It is the fully constrained member, how we are going to be developing the imaginary forces. So in this example I have taken fully constrained body. What is the fully constrained body here? There we can see in the last problem only we have taken. So A and B is going to be the member of the bar and it is hinged at C. So once it is hinged means the load of the P is going to be acting in this direction. It's trying to rotate about the hinge C. So but what I am going to do, I am applying the one more support over here. That's going to be say AB is the one member I was added over here. So then what will happen? The rotational motion or the moving up and downward direction of the NDA is going to be restricted by the AD. So now what I am going to be do here, I am going to be find out the virtual motions. So then what will happen? This is completely constrained. That means fully constrained means the body cannot move in the downward direction or upward direction. But how I can develop the virtual work? So in this case what will happen? I am going to be removing this AD member. I am going to be show with the internal force. So once I am going to be removing the member and showing with the internal forces, then we can make to move the body in the upward direction as well as the downward direction, or we can make to rotate about that point. So how I am going to be taking? I am going to be taking the axis of this member only. So then what will happen here? That I am going to be taking the axis of the member. This is the end A and this is the end B and this is the point C we do have. So this is going to be considered the skeleton diagram of this the bar AB. So then what will happen in this case? So this I am removing the member of the AD that I am going to be shown with the internal forces which is going to be acting in the downward direction. That is the FAD I am going to be considering. And the distance is the A, and between the BC is going to be the D is there, so B, and here is the force P is going to be active. So then, as usual, we are applying the virtual displacement. So through this one, I am going to be taking like this. So this is going to be your virtual displacement, and it is going to be making an angle of del theta, and here also del theta it is going to be making, right? And A dash is going to be coming over to the here. And B dash is going to be coming to here. So as usually we can calculate that this is going to be the A and the B. So if I am going to be taking the total work done by the system, that is equal to 0, the total work done W dt is equal to 0, total work done, because of the force, internal force, and this is the P. So this force is going to be moving in the downward direction and the displacement also in the downward direction, means the work done because of the FAD is going to be 0. And here is the P force is going to be acting, it is in the downward direction, but the displacement is in the upward direction. So that I am going to be taking FA dash, here is the FAD, this is the infinitesimal imaginary displacement minus P into B dash is equal to 0. So then as usual FAD, that's going to be A into del theta, that is going to be P into B into del theta I am going to be taking. This del theta is going to be cancelled mathematically. Then FAD into A, that's going to be P into B I will get. Right? So from this force, what will happen? We are going to be calculating the internal forces of this member. We are going to be that is the AD internal forces we are going to be calculating, or any other forces. Suppose if you know the internal forces of this member, then we can calculate the force at the external forces acting at B. Also we can calculate. This way, the principle of virtual work is going to be applying for the different members, and we are going to be calculating the internal forces of this member. So what we learn from this one? The first one we do have taken, when the body is in the equilibrium condition, then how the virtual displacement we can generate from that. And the case 2 is going to be fully constrained body is there. Then we learn how to remove the one part of the body which makes you fully constrained of that body, that we removed it, and that means it shifted from the equilibrium condition. Then we shown with the one internal force, and then we applied the virtual displacement, and then we calculated as usual. Thank you.